So, Bill, last time we talked, I think you made some statements about code verification versus solution verification. So today in our conversation, I'd like to understand that a little bit better. And I want to describe maybe a scenario, and then you can kind of tell me, where does that fit with regards to those verification activities. So our commercial software provider, they publish these verification problems. And as a part of our verification activities, we run a suite of those problems covering the kinds of physics that we're using. And we do that anytime we upgrade the simulation software or anytime we upgrade our operating system. And so it's kind of a do it once until the next time, triggers an upgrade. So how does that fit with your definition of verification, and particularly, is that probably more code verification than it is solution verification?
Yeah, let me for people that are just tuning in, to get everybody on the same page here, the two issues that we've been talking about are verification and validation. And the verification has the two aspects that you mentioned, code verification and solution verification. Sometimes solution verification is called calculation verification, and that's a fine term. And the verification, both code and solution verification, deal entirely with estimating or finding numerical errors. It has nothing to do with the assumptions, the physics assumptions in the construction of the mathematical model. It's entirely software and numerical approximations, convergence, order of accuracy, all of those kinds of things. So this has nothing to do with physics. Given the physics model, then we have differential equations that we cannot solve analytically, so we solve them approximately with numerical methods, which are then implemented in software. So, and the question you asked on code verification, when mostly the code verification is done by the software companies themselves or whatever group is developing the software, and that's a primary responsibility that they have. But the responsibility also is shared by organizations like yours, that once you get in, let's say, a new version of software package, then you should do some basic testing on the test problems that are important in your environment. And these would be, they can be code verification test problems, which means on code verification, you have an analytical solution and an exact solution to the mathematical model. Mathematical model is the calculus problem. And so that's what we're talking about, doing code verification testing. And then on the solution verification testing, that's an entirely different activity. In solution verification, it is error estimation for a given mathematical model. And then we solve that discretely with finite elements, finite difference, finite volume, whatever we do. And so that solution verification is done on the individual problems that we are solving for. And usually it's called the application of interest or the system of interest. So maybe that helps, Greg.
Okay. On that solution verification, can you explain a little bit more? Is that, getting things like mesh independence, discretization type error, and evaluations of those kinds of error, or am I off base there?
No, that's exactly right. In solution verification, you have a couple of elements of where errors might come from. The most common ones that we're talking about here are those due to discretization from finite element, finite volume, whatever the method is. And these are discrete methods in the sense that they discretize the original differential equation, and then we iteratively solve those equations. Okay, those equations are all arithmetic equations. They're not calculus problems. So they approximate the calculus problem. And as is well known in numerical methods, these numerical methods have a truncation error. It can be called a discretization error, but it's usually called truncation error because it is an approximate solution. And as the mesh is refined, whatever discrete method you're using, as the mesh is refined, then the solution should converge to the correct solution in the sense of the same solution to the calculus problem. And that's one of the tests that you always should do. One of the difficulties is in relatively large scale problems, these finer and finer meshes get very expensive and you can't afford to do that. And that's especially true in three-dimensional problems. And of course, it gets even worse in three-dimensional unsteady problems like deformation of structures like in a car crash or some sort of dynamic environment. So those are some of the practical difficulties of trying to do solution verification.
Okay. So what resources are available that help us decide what's a reasonable trade-off between these activities?
Okay. Well, on the code verification, let me answer it first on that one. Code verification is entirely a testing process of the software and the numerical methods. And I say testing as opposed to an estimation problem. It is not an estimation problem. It's a testing problem of the software and the algorithms because you must have an exact solution to the mathematical problem. And so the common procedure is what you had talked about, where you test them when there is a new version of the software. But also, if you're considering a new software package, you should talk to the software vendor and ask them, what is their code verification data set? Show me all of the code verification problems that you have tested. And then you can see how they relate to your problems of interest. And then if you have some exact solutions that you want to test it on, you could test the software on a trial basis. And then on solution verification, that is typically a much more involved endeavor because you have numerical approximations, there's discretizations error, there is also iterative errors, those are separate, okay, from discretization. And then there's also a sampling. If you're doing a non-deterministic simulation, then you also have sampling errors. And also in the solution verification, if a analyst makes an error in the input data for the model, that error is actually called part of the solution verification error. So those kinds of things also should be considered because that happens relatively often. But that, of course, is a user error, and the best way to check that is have other users or check your own work and have others check it. So people need to realize there are a number of sources of errors that go into solution or this calculation verification.
Okay. And are there specific resources, either standards that govern what needs to happen for various industries or applications, or otherwise, publications of best practices that would help the beginner figure these steps out?
Mm-hmm. Yeah, that's a good practical question. One of the things that you should expect from your software vendor is ask them what sort of error estimation tools do they have with their software package. And when we say error estimation, we're talking about solution verification. They may also have tools, and there the emphasis is on discretization error. But then they also may have estimators on iterative error, like on a boundary value problem, an elliptic problem. Suppose that this is a steady state, let's say a stress problem or a fluid mechanics problem, in all steady state. Then since that's a nonlinear set of discrete equations, you have to iteratively solve them, okay? And then there's a separate error due to discretization. So you should ask your software vendors, what tools do they have to estimate the error in the system response quantities that you're interested in your particular solution? And so those are tools that you should reasonably expect from the software vendor. Some vendors do better than others. For example, in solid mechanics, essentially every vendor has an error estimator based on the global error. It's usually called a global energy norm. It's an error over the entire it's usually in terms of strain energy, over the entire domain, solution domain. And that is an excellent first step, but you have to realize that norm is over the entire domain. It doesn't tell you what the error is locally. It tells you what the estimated error is over the entire domain.
Okay. So I think that's some helpful guidance for software tools or specific from software providers. How about like NAFEMS publications or regulatory standards? Are there specific guidances provided there, or is this still largely up to us to define what is the best practice?
Yeah, that I think there's some weaknesses there. You could say that there are textbooks that are on this topic, but there are not many publications that actually deal with it in any kind of detail, in the sense of what kind of numerical error estimators, solution verification estimators might be useful. There are publications in various journals and conference papers, but in my opinion, there are not a lot of, there's some guidance that ASME has on the various aspects like code verification, solution verification, validation, and so on. And NAFEMS also have some in that regard, but it's not a topic that has been, I'd say, widely explained and what tools might be available. So I think some improvements are needed there.
Okay. So I guess my final quick question would be is if you could convince everybody to do one thing related to verification, what would that be?
Okay, well, Greg, I want to cheat on you a little bit. I want to give you two things. One of them is on code verification. On code verification, check what the software vendor or the software developer has on what test problems they have. Those are analytical solutions, okay? They can be a class called manufactured solutions. Those are excellent. And so check what their code verification test problems are. And when I say check, see if they demonstrate convergence with mesh discretization and also iterative as the mesh is continually resolved. So that's something you should do on the code verification side. On the solution verification side, you should ask your software provider what tools are available there, and you should use those tools if they have them. If your software provider does not have, let's say, a local error estimator, like what's an estimate of the local stress, or if it's a fluid mechanics problem, the local estimated, this is all numerical error, this isn't physics, the local estimated error in local pressure or temperature or shear stress, or on other local quantities like local heat flux, then if the software provider does not have that, then your organization, your company should start thinking about how do you build those to add on if you can't get your software provider to build them. Because we have found in years past, many people have found that when even experienced analysts are doing solution verification, they think they have converged solutions, and then when they get a bigger computer and they do more solution convergence in the sense of finer meshes, they realize that the solution changes again and again. And that's something that can really burn you, because you think you have the solution to the mathematical problem, but you really don't. So those are the two suggestions I would make, Greg.